Hey everyone, in this section we're going to go over solving systems of two equations and two unknowns with a method of elimination. So, with the when we were solving by graphing, it was convenient to put our equations into y equals mx plus b form, slope-intercept form, because that was a convenient method to graph. For substitution, we were just trying to get one of the variables by itself. We tried to get y by itself or get x is equal to something, and then we're trying to plug it in. For the method of elimination, you want to write both of your equations in standard form. Both equations in ax plus by is equal to c form. So, let's start with an example. Let's say we had 2x minus 3y being equal to 0, and negative 4x plus 3y being equal to negative 1. Notice, so a couple things to notice off the bat. It's not really convenient to solve for one of these variables. We're going to introduce a bunch of fractions if we try and get x or y by itself in the top equation, and same thing with the bottom. These lines also might not intersect in convenient locations. So we want to come up with another algebraic method that's easy to work with these equations in the form that they are. So first, make sure that you've got all your x's stacked on top of each other, and all of your y's stacked on top of each other, and your equal sign and your constants. And also, notice how in this top equation, we've got a minus 3y and a positive 3y. That's the trick for solving by elimination. You want to come up with you want in your pair of equations, you want to find coefficients that are opposite in sign, but equal in magnitude. Like you want to find a minus 3 and a positive 3. So what we're going to do is we're going to take both equations, 2x minus 3y is equal to 0, and negative 4x plus 3y is equal to negative 1. And what we're going to do is we're actually going to add these equations together. And we're going to add in columns. So 2x plus negative 4x gives us a negative 2x. Negative 3y plus 3y gives us plus 0y. And 0 plus negative 1 is equal to negative 1. I'm just going to rewrite this equation as negative 2x is equal to negative 1. Well, we're trying to get x all by itself, so let's divide both sides by negative 2 to get x is equal to negative 1 divided by negative 2 gives us a positive 1/2. And that's what I should have put a box around. Just like with the other methods, once you had one value, it didn't matter which equation you plugged it into to come up with the second. That rule still applies here. I'm going to choose the top equation. We know that 2 times x minus 3y has to equal 0. We know that x is equal to 1/2. That means 2 times 1/2 minus 3y has to equal 0. 2 times 1/2 is 1. Minus 3y is equal to 0. We could subtract 1 from both sides to get negative 3y minus 1 is equal to negative 1. And finally divide both sides by negative 3 to get y being equal to a positive 1/3. And remember, solutions to systems of equations with two variables is a point. So that point, xy, that is the solution to this system of equations, or you can think of it as the point where these two lines intersect, is the point 1/2, 1/3. This is going to be our overall process for solving systems of equations by elimination. This is also the preferred method for solving larger systems of equations. That is until, if you guys ever take linear algebra, you'll discover a lot of other techniques for solving systems of linear equations. But for now, we're gonna keep our focus mainly on just solving two equations with two unknowns for now. You want to find two variables. You might also be forced to create two variables. that have leading coefficients whose numbers are opposites of each other, and then you add both left-hand sides of the equations with both right-hand sides of the equations with the idea that you're going to get rid of one of those variables. This is where the elimination comes in. You're eliminating one of the variables. You're left with one equation and one unknown. You solve for that variable. Once you have its value, you plug it back into either of the equations. We chose the first one. We could have done the second one. And you solve for your second value. And remember, our solutions are points. So let's consider another example. Let's say we've got the system of equations 3x plus 3y is equal to 15 and 2x plus 6y is equal to 22. Now in the last problem, we had these terms whose signs were opposite. They had the same number, but their sign was opposite. We don't have that same thing here. We do have our column of x's, our column of y's, and our constant column though. Now, you can take an equation and you can multiply both sides of that equation by any number you want to, any non-zero number. You can multiply both sides of the equation by 0 too, you just erase any information you had. And what we want is we want two numbers, like in this first example, whose signs are opposite. Well, if you look at that top equation, we can multiply both sides of this equation by negative 2. We'll put a negative 2 and a negative 2. Well, negative 2 times 3x will give us a negative 6x. Negative 2 times 3y will give us a negative 6y. That'll be equal to negative 2 times 15 gives us a negative 30. This bottom equation we haven't changed, so I'm just going to rewrite it. 22. And now look at what we've done. We haven't changed the values of x and y that make this statement true by multiplying both sides by negative 2. But what we have done is we have introduced leading coefficients that are opposite in sign. We've got this negative 6y, and we've got this positive 6y. So now that we have that, we've got coefficients whose numbers are the same but signs are opposite. We can add both sides of these equations together. We can take negative 6x minus 6y being equal to negative 30, and we can take 2x plus 6y being equal to 22, and we can add these equations together. Negative 6x plus 2x gives us a negative 4x. Negative 6y plus 6y gives us a plus 0y. That equal sign drops down. And negative 30 plus 22 gives us a negative 8. I'm going to rewrite this equation without the 0y. Negative 4x is equal to negative 8. Divide both sides by negative 4. And we get x being equal to a positive 2. Once we know what x is equal to, it doesn't matter which equation we plug it into. Top one or bottom one, they both will give us the same value for y. Let's try the bottom one. If 2 times x plus 6y is equal to 22, well that means 2 times 2 plus 6y has to be equal to 22. 2 times 2 is 4 plus 6y, which is equal to 22. Subtract 4 from both sides to get 6y is equal to 18. Divide both sides by 3. Get y is equal to, divide both sides by 6, I'm sorry. To get y is equal to 3. So, this is our process. Well, this isn't our final solution because our solution isn't just some values put in a box. It's a point x, y, and the point where those two lines intersect is going to be the point 2, 3. So what really deserves the box is that 2, 3. This is going to be our solution to this system of equations. We haven't done it yet, but let's go through and check our work. Let's make sure that 3x plus 3y is equal to 15, or that 3 times 2 plus 3 times 3, is that in fact equal to 15? Well, 3 times 2 is 6, plus 3 times 3 is 9. And we go, yeah, 6 plus 9 is totally equal to 15. 15 is equal to 15. That bottom equation said that 2x plus 6y had better equal 22. Well, we want to make sure that 2 times 2 plus 6 times 3 is that in fact equal to 22. 2 times 2 is 4, plus 6 times 3 is 18. Yeah, 18 plus 4 is definitely equal to 22. So our solution checks out. The trick on this problem was we didn't have the thing that we needed, for lack of better terms. So what we did was we multiplied both sides of this top equation by -2, so we could get terms whose signs were opposite. Looking at this problem, there is nothing wrong with, and I'll write down here, we started off with 3x plus 3y is equal to 15, and 2x plus 6y is equal to 22. Before we modified that top equation, but we could have modified this bottom equation. We could have multiplied both sides of this bottom equation by a -1/2. And what we do to one side, we have to do to the other. -1/2 times 2x would give us a -x, and -1/2 plus 6y would give us a -3y, and that'd be equal to -11. And that top equation, 3x plus 3y is equal to 15. Well, if we were to run through this real quick, this would say that 2x would be equal to 4, and x would be equal to 2. Doesn't matter which equation we modify, we go through, plug x is equal to 2 back into either of these equations, and we'd still get y being equal to 3 when we're done. So we're just looking to find some way to get what we need. These leading coefficients that are opposite in value. Sometimes we're going to need to modify both equations. So let's consider the system of equations. 2x plus 3y is equal to 17, and 5x plus 7y is equal to 29. Now in our previous example, all we had to do was modify one equation to get these leading coefficients with opposite signs. In this next example, I mean, we could multiply 2 by -5/2, but I don't necessarily like to introduce fractions unless I absolutely have to. We can, however, multiply both of these equations by a different value if need be, to make leading coefficients opposite in sign. So I'm looking at these x's. We've been eliminating y's a lot, so I'm looking at these x's. And just picking one, I'm going to take this top equation, and I'm going to multiply both sides by 5. 5 times 2x would give us 10x, plus 5 times 3y would give us 15y, is equal to 17 times 5, 5, 6, 7, 85. With this bottom equation, I'm actually going to multiply both sides by a -2. Multiply by -2. -2 times 5 gives us a -10x. -2 times 7 will actually give us a -14y. And that's going to be equal to 29 times -2. That would give us a negative, that would give us an 8, and that would give us a 5. Perfect. Yeah, perfect. And if you look what we did, by multiplying that top equation, both sides of it by 5, we got a positive 10x. And by taking that bottom equation, multiplying both sides of it by -2, we got a negative 10x. So we're going to go through, and we're going to add these two now. 10x plus negative 10x, that gives us a 0x, plus 15y take away 14y gives us y. Oh, and then 85 minus 58. We'll subtract those. Oh, we'll turn that into a 7. That gives us a 7 and a 2. So y is equal to 27. Once we've figured out the value of y, we're free to plug it into any of the equations we have so far. Remember, any values that make these bottom equations true will also make these top equations true. If you guys are using a calculator, it really doesn't make a difference which one you pick. I'm going to choose this top equation because I'd much rather multiply 27 by 3 instead of multiplying 27 by 7. So, if 2x plus 3y is equal to 17 and y is equal to 27, that means 2x plus 3 times 27 had better be equal to 17. Oh, 27 times 3, 7, 14, 21, 6, 7, 8. We get 81. So 2x plus 81 had better be equal to 17. Well, if we take 81 and subtract 17 from it, that's a 7, that's a 1, so that'd be a 4, 64. And it would be a negative 64. So we get 2x to be equal to a negative 64. Divide both sides by 2. So you get x being equal to a negative 32. Which, it'd be best if we went through and we checked this work. I've got the answer written down off camera, so I know I did it right. But this process, this is as complicated as these problems get, at least in theory. We had to multiply both sides of this equation by some value to get these leading coefficients that are opposite in sign. But once we did that, we were able to add these two equations together to eliminate a variable and solve from there. It doesn't matter, like I chose to multiply both sides by 5 because I try and find the smallest numbers I can use to multiply things by. Especially when I'm effectively doing math live. I try and make as few mistakes as possible. We could have taken these equations, 2x plus 3y is equal to 17, and 5x plus 7y is equal to 29. And we could have, say, multiplied this top equation by negative 7, and this bottom equation by 3. That would have given us negative 14x minus 7, 14, 21y is equal to 7, 8, 9, 10, 11, negative 119. And this bottom equation would have became 3 times 5 gives us 15x plus 21y is equal to 27, 87. Would have gone through and added these equations. X would have been equal to negative 32. So there's more than one approach to these problems. What number do you multiply by is going to depend largely on which problems, and there's going to be some that are easier than others. If you noticed, I had this 2x and this 5x. I multiplied the top by 5, the bottom by negative 2. Over here, I had a 3y and a 7y, multiplied the top by negative 7 and the bottom by 3. I'm really taking this number and multiplying the top equation by it, and this number and multiplying the bottom equation by it, and I'm making one of those negative. That's a method. A lot of times you're going to hear people talk about you want a least common multiple of the two. There's a lot of emphasis on a least common multiple. For the sake of doing math for practical skills, you don't necessarily need a least common multiple. You just need a common multiple. So another skill, another something I want you to be aware of is notice how we multiplied both of these equations by some value to make it so they were easier to combine. We can also take a system of equations, say 0.2x plus 0.3y being equal to 1.7, and 1 over 7x plus 1 over 5y being equal to 29 over 35. And as you see, we've got decimals and fractions. It's good practice to try and clear out decimals and fractions, especially while you're learning. It makes the numbers a little bit easier to work with. Doesn't matter if you're using a calculator. Not really. A calculator does not care. But, it's good to practice math by hand. It teaches intuition. It shows you how it'll help develop intuition about how numbers relate. So let's clear out these decimals to make them easier to work with. And let's clear out these fractions. Well, if you notice, I just got to bump this decimal point by 1 to the right for every value in that top equation. So I'm going to multiply both sides of this equation by 10. And if you look over here, well, I've got a denominator of 5 and a denominator of 7. Their least common multiple is 35. I'm going to multiply both sides of this equation by 35. This top equation, bump that decimal, becomes 2x plus, bump that decimal, 3y is equal to, bump that decimal, 17. And this bottom equation, well, 35 divided by 7 becomes 5x plus 35 divided by 5y becomes 7y is going to be equal to 35 cancels out with 35, 29. If you look, this equation is now the same as this equation that we did a moment ago, and it'll have the same answer of negative 32, 27, because though I didn't write it over here, we know that solutions to system of equations with two variables is a nice point, good coordinates x and y. We're not going to continue working this example, it's all done over here, but this was to illustrate the fact that sometimes you might want to bump decimals and clear fractions in order to make the equations easier to work with. Your first step does not have to be making signs opposite. You can take a couple smaller steps through a problem, and especially if that makes it so you make less mistakes, then sounds like a great approach to the problem to me. There's always a huge emphasis on doing everything right with the first hit. But don't be afraid to take a couple steps through the problem before it becomes clear to you how you can proceed. So just like last time, systems of equations can either have, systems of linear equations can have either one, none, or infinitely many solutions. I want to give you guys examples of what it looks like when a system of equations, or when you solve a system of equations with the method of elimination, and your solution in your system gives you no solution or infinitely many. So first, let's consider the system y plus 3x is equal to 5 and y plus 3x is equal to negative 2. Now we've got our y column and we've got our x column. Doesn't matter if our x column comes first or second. The thing that's important is that you have the same variables stacked on top of each other. And let's go through. We want to make coefficients opposite in sign. So let's take this top equation, multiply both sides by negative 1, and get this equivalent system. Negative y minus 3x is equal to negative 5, and y plus 3x is equal to negative 2. We've got coefficients that are opposite in sign, so let's go through, let's add them. Negative y minus 3x is equal to negative 5. Negative 5. And y plus 3x is equal to negative 2. When we go through and add these, our y's are going to cancel, and our x's, and we're going to be left with 0 is equal to negative 7. 0 is definitely not equal to negative 7. This is a false statement. And just like before, false statements mean that this system has no solution. Just like with substitution in elimination, false statements means no solution. Now if we had, say, 3y minus 2x being equal to 6, and negative 12y plus 8x being equal to negative 24, this system of equations. Well, I noticed that if I multiply this top equation by 4, 3 times 4 would give us a positive 12, and we've got a negative 12 down here. So let's plan on trying to eliminate these y's. Multiply this top equation by 4, both sides, and we can get an equivalent system of equations of 4y minus 8x is equal to 24, and, that would be 12y minus 8x is equal to 24, and negative 12y plus 8x is equal to negative 24. Well, we've got coefficients that are opposite in sign, so let's go through and add these two equations together. 12y minus 8x plus 24, and negative 12y plus 8x. And I said equals negative 24. Go through and add these two together. 12y plus a negative 12y gives us a 0y. Negative 8x plus 8x gives us no x's. And 24 plus negative 24 gives us no constants. This equation reduces to 0 equals 0. A true statement. A true statement regardless the value of x's and y's. When we have statements that are true regardless the value of x and y, that means our system has infinitely many solutions. Just like with the method of substitution, with elimination, false statements are no solution. True statements are infinitely many solutions. So let's do a final example, and let's let this one be a story problem. Just like with substitution, any system of equations story problems, keep your ears out for two different statements about how quantities relate to each other. So, to stimulate the economy in his hometown of Brunton, Alabama, in 2009, we've got this pharmacist. He gave each of his full-time employees $700. $700 to full time. And he gave $300 to each of his part-time workers. Okay? He also asked that each person donates 15% to a charity of their choice, and the rest they wanted to spend locally. The story goes on to say the money was paid in $2 bills, a rarely used currency, so that the business community could easily see how the money circulated. This person gave away a total of $16,000. $16,000 to their 24 employees. How many full-time employees and how many part-time employees were there? So I'll read it again. To stimulate the economy in his hometown of Brunton, Alabama, in 2009, Danny Cottrell, co-owner of the Medical Center Pharmacy, gave each of his full-time employees $700 and each part-time employee $300. He asked that each person donate 15% to charity of their choice and spend the rest locally. Money was paid in $2 bills, a rarely used currency, so that the business community could easily see how the money circulated. Cottrell gave a total of $16,000 to his 24 employees. How many full-time and how many part-time employees does he have? Well, that 15% actually doesn't come into play in this problem. But what we do know is we know information about the number of employees and how much money was given out. So I'm going to say we're going to let X be the full-time, the number of full-time employees, and Y is going to be, we can use an equal sign, number of part-time employees. So we know that the number of full-time employees plus the number of part-time employees is equal to 24. That's how many people he has employed. And we know that $700 times the number of full-time employees plus $300 times the number of part-time employees equals $16,000, or the total amount of money the pharmacist gave out. Well, now we've got two equations with two unknowns we can solve for them. We've been doing the process of elimination, so we'll continue with that method here. Oh, it doesn't, I could either multiply both sides of this top equation by 700, or I could multiply both sides of this equation by, negative 700 or negative 300. I'm going to choose negative 300 just to keep my numbers smaller. This becomes, so negative 300 times x gives us a negative 300x minus a 300y. Oh, and 300, well, 24 times 3, that's 12,672. So I tack on 2 zeros there, and I get a tack on 2 zeros there. So is equal to a negative 7,200. And this bottom equation stayed the same. 700x plus 300y is equal to 16,000. Well, now we've got two equations. One of the variables, they have a sign that is opposite. Let's use the method of elimination. That's where we take negative 300x minus 300y being equal to negative 7,200. And we'll add 700x plus 300y equals 16,000. We're going to go through and add these. 700 take away 300 leaves us with 400 x's plus 0 y's. Oh, 16,000. We can work over here. 16,000 minus 7,200. Oh, we'll turn that to a 5. We'll turn that to a 10. 0, 0, 8. 8 is equal to 8,800. Well, 400, that tells us that 400x is equal to 8,800. Divide both sides by 400. Divide both sides by 400. X is equal to, well, 4 goes into 8822 times. Once we know what x is, we know that x plus y is 24. That tells us that 22 plus y had better be equal to 24, or y is equal to 2. Remember, this is a story problem. The problem is asking about full-time and part-time employees and not the value of some variable we made up, x and y. So we know that there are 22 full-time employees and 2 part-time employees.